$25 billion. 400 kilometers of tunnel, buried beneath the most hostile ocean on Earth. The Arctic ice sheet moves 3 meters every day, grinding everything to dust. Pressure ridges crush steel like aluminum cans. Temperatures hit -50 Celsius in darkness that lasts 4 months. And somewhere under all of that, engineers built a tunnel that was not supposed to exist. In this video, you will see how autonomous robots, self-healing materials, and AI construction crews built a tunnel where humans cannot survive. You will see the design that made it possible, the crisis that nearly destroyed it, and the technology that turned the Arctic into a transportation corridor. But first, you need to understand why this is the worst place on Earth to build anything. The Arctic Ocean is not like other oceans. Pack ice drifts in massive sheets driven by currents and wind. Pressure ridges form where ice collides, piling blocks the size of houses 30 meters high. Below surface, those ridges extend downward like inverted mountains, reaching depths of 50 meters. The water hovers at -2 Celsius, thick with ice crystals. Any structure ices over in minutes. The cold changes how materials behave. Steel becomes brittle, rubber shatters, electronics fail, even the seafloor shifts. Permafrost extends hundreds of meters down, heaving as it freezes and thaws. Then there is isolation, 1,000 kilometers from the nearest city. Supply ships operate 3 months a year when ice retreats. For 9 months, you are alone. No resupply, no rescue. If something fails, you solve it yourself or abandon everything. This is where engineers decided to build a 400-kilometer tunnel connecting 2 continents. The question was not whether it was possible. The question was how. Engineers faced 3 designs, each with fatal flaws. Option 1, a seabed tunnel in prefabricated sections lowered to the ocean floor. The problem was ice. Pressure ridges extend so deep they would scrape directly across it, ripping it apart within years. Forces measured in megatons. No structure could survive. Option 2, a deep bored tunnel drilled through bedrock 300 meters below the seafloor, isolated from ice and water. Safest design, but tunnel boring machines would advance 10 meters per day. 30 years and triple the budget. Technically possible, economically impossible. Option 3, a suspended subsea tunnel hanging in the water column, held by cables anchored to bedrock. The tunnel would float at 150 meters depth, well below the deepest ice keels. Elegant, radical, never proven at this scale. The engineers chose the floating tunnel, not because it was safe, because it was the only option that could be built within realistic timeline and budget. Decision made in 2032. Construction started in 2035. First segment touched water in 2037. Before building, engineers mapped the seafloor with precision no human crew could achieve. Autonomous drones deployed in swarms of 50, equipped with sonar and ground-penetrating radar. They worked in winter darkness, scanning bedrock for faults and fractures. Every square meter of the route was mapped with centimeter accuracy. The data revealed the problem. Seafloor varied dramatically. Solid granite in some sections, soft clay extending 100 meters in others. Anchoring would need to adapt. Robotic drilling rigs punched core samples 300 meters into bedrock. Each core revealed granite composition, fracture density, water permeability. AI calculated exactly where each anchor could be placed and what load it could hold. No margins for error. If one anchor failed, tension would redistribute through the cable network. Too much redistribution and the tunnel section would tear free and sink. Anchor installation was fully autonomous. At 150 meters depth in freezing water with zero visibility, human divers would die within minutes. Drilling robots descended on tethered cables, their manipulators guided by AI. Each anchor, a titanium shaft driven 15 meters into bedrock, locked with expanding grout. Load capacity per anchor, 5,000 tons. Number of anchors, 800. Total drilling time, 14 months. While anchors were being installed, the real engineering challenge was being solved 2,000 kilometers away in a shipyard on the Norwegian coast. This is where the tunnel segments were being built. The tunnel segments were built 2,000 kilometers away in a Norwegian shipyard. Each segment, 50 meters long, 15 meters wide, 12 meters tall. Weight, 4,000 tons. The walls were composite structures, outer skin of ultra-high performance concrete reinforced with basalt fibers. Middle layer of closed cell foam for insulation and buoyancy. Inner skin of steel-lined concrete for pressure containment. Between layers, embedded sensors and self-healing channels filled with polymer resin that would automatically seal cracks. Each segment took 6 months to build, 8 in production simultaneously. Once complete, segments were towed north on transport barges. Journey time, 3 weeks. Arrival timing was critical. Too early and segments sat idle. Too late and the weather window closed. Installation was the most dangerous phase. The segment arrived floating, ballasted with seawater. Autonomous tugs maneuvered it over anchor points using differential GPS accurate to 2 centimeters. Then came cables. Robotic submarines attached 16 vertical cables, each connecting seafloor anchors to hardpoints in the tunnel. The connection used fail-safe hydraulic couplers that engaged only once. If it missed, the entire cable needed replacement. Once cables attached, ballast water pumped out. The segment rose, pulling cables taut. Tension increased over 6 hours until the tunnel reached operational depth of 150 meters. The segment now hung suspended by 400 tons of tension per cable, floating weightlessly like an underwater bridge. Individual segments mean nothing. The tunnel only works when they connect into a continuous sealed corridor. Traditional tunnel joints use rubber gaskets and bolts. They fail underwater. Rubber degrades, bolts corrode, gaskets leak. The Arctic tunnel used smart joints. Each segment ended in a precision-machined flange, flat to 1/10 of a millimeter. When 2 segments approached, robotic arms positioned them within centimeters. Then, electromagnets activated, pulling segments together with 50 tons of force. As flanges met, thermoplastic polymer melted from friction heat and flowed into microscopic gaps. Within 60 seconds, it solidified into a seal stronger than concrete. Around that, expanding foam filled every void. Around that, fiber-reinforced epoxy cured with UV light. The result? A joint that could flex several centimeters for thermal expansion, yet remain watertight under 15 atmospheres. Each joint took 18 hours, 700 joints total. Joining time, 13 months. The tunnel needed active ventilation. 400 kilometers is too long for simple circulation. Massive fans at both ends pushed fresh air through the tunnel, with exhaust vents every 5 kilometers. Power came from distributed sources. Every 10 kilometers, a vertical shaft extended up to a floating platform locked into surface ice. Each platform carried a 20-megawatt modular nuclear reactor, passively cooled by seawater. 20 reactors total. If one failed, others compensated. Fire safety was existential. A fire produces smoke faster than ventilation clears it. The system used fire-resistant materials, infrared cameras every 100 meters, automated water mist suppression, and pressure doors every 2 kilometers. A fire in one zone could not spread. Passengers in adjacent zones evacuated through parallel escape tunnels. Evacuation was designed for worst case. The main tunnel carried vehicles. Running parallel, offset by 20 meters, was an escape. Tunnel connected every 500 meters by cross passages. If the main tunnel flooded, passengers had 30 seconds to reach a cross passage. Once in the escape tunnel, illuminated pathways led to the nearest vertical shaft. Survival time in water, 2 minutes. Survival time in escape tunnel with thermal blankets and oxygen, 72 hours. The tunnel floats at 150 meters. Deepest ice keels reach 50 meters. That leaves 100 meters of safety margin, on paper. In reality, ice is unpredictable. Every segment carried upward-facing sonar, continuously scanning ice above. If deep ice approached, the system calculated trajectory and depth. If it threatened within 80 meters, automatic response activated. Ballast tanks flooded with seawater, pulling the affected section 10 meters deeper. Tension cables allowed the descent. Once ice passed, ballast pumped out, and the tunnel returned to operational depth. fully automated. Human response was too slow, but what if ice was too deep or too massive? The tunnel had sacrificial bumpers. The top surface was covered with 5 meters of crushable foam designed to absorb impact energy. If ice struck, foam would compress and spread impact over a larger area. The foam was replaceable. The tunnel was not. Over 5 years, the tunnel descended 6 times to avoid ice. Foam absorbed minor contact 4 times. The system worked. Human workers built the first tunnels in history with pickaxes and dynamite. Human workers built the next generation with tunnel boring machines and concrete forms. Human workers did not build this tunnel. They could not. The environment does not allow it. Instead, humans designed the systems. Robots did the work. The construction fleet included 60 autonomous underwater vehicles, 40 surface vessels, and 20 airborne drones. Each AUV was a mobile sensor and manipulation platform capable of drilling, welding, cutting, inspecting, and repairing without direct human control. AI coordinated the fleet, assigning tasks, optimizing paths, and predicting failures before they occurred. A human crew of 80 people based on surface vessels and ice platforms supervised the robots remotely, intervening only when the AI encountered a situation outside its training data. That happened less than you would think. Predictive maintenance was the key to keeping the project on schedule. Every robot carried accelerometers, temperature sensors, and acoustic monitors that listened to their own mechanical health. Bearings that were starting to wear produced a specific frequency signature. Hydraulic seals about to fail showed pressure fluctuations. The AI learned these patterns. When a robot was projected to fail within 48 hours, it was automatically pulled from service and sent to a maintenance barge for repair. Failures in the field, underwater, in freezing darkness. 0. The most advanced robots were the joint sealing units. Each one was a 6-armed autonomous system, working in pairs, one on each side of a joint. They communicated through acoustic modems, coordinating their movements with millisecond precision. While one robot positioned the thermoplastic ring, the other prepared the epoxy applicator. While one cured the seal with UV light, the other inspected with ultrasonic sensors. They worked faster than humans, more accurately than humans, and in conditions that would kill humans in minutes. They were not replacing workers. They were doing jobs workers could never do. Construction progressed for 4 years, 350 kilometers completed, 50 kilometers remaining. And then the system detected an anomaly. A tension cable on segment 214 showed a load increase. Not catastrophic, just 3% above nominal, within design tolerance. The AI flagged it. Human engineers reviewed it. They cleared it as acceptable variance. That was the mistake. Over the next 6 days, the load increased to 8% above nominal, then 12%, then 18%. The cable was not failing. The anchor was shifting. Bedrock that had tested as solid granite was fracturing under sustained load, allowing the anchor to creep upward by millimeters per day. If it pulled free, the load would redistribute to the other 15 cables on that segment. They would overload. The segment would drop. The joints on either side would fail. A 100-meter section of tunnel would flood and sink. The AI proposed a solution humans would never have considered. Instead of trying to repair the anchor, which was impossible without draining the ocean, it would install a new anchor, offset by 50 meters, and transfer the load gradually. An AUV was dispatched. It drilled a new anchor point in 72 hours. A second AUV installed the anchor hardware. A third connected a new tension cable to the tunnel segment, leaving it slack. Then, over 48 hours, the AI slowly increased tension on the new cable while decreasing it on the failing anchor. The load transferred smoothly. The old cable was cut. The segment stabilized. Crisis averted. Total human intervention, supervising the AI's plan and approving the execution. The AI had solved a problem that would have taken human engineers weeks to even analyze. The final segment was installed in 2041, 6 years after construction started. 400 kilometers of tunnel suspended in the Arctic Ocean, connecting 2 continents for the first time in human history. But installation was not completion. The tunnel needed to be tested. Pressure testing came first. Every segment, every joint, every seal was pressurized to 20 atmospheres, 50% above operational maximum. Inspectors, both human and robotic, walked the interior, scanning for leaks with thermal cameras and acoustic sensors. They found 12 minor seeps in joints. Repair robots injected epoxy patches. The leaks stopped. Total water intrusion, less than 10 liters. Acceptable. Ventilation testing followed. Fans at both ends spun up to full power, pushing air through the 400-kilometer corridor at 15 kilometers per hour. Smoke generators released harmless tracer particles. Sensors tracked dispersion. The system cleared smoke from a 2-kilometer section in 11 minutes. Fast enough to save lives. Fire testing was the most dramatic. In a sealed test section, engineers ignited a controlled fuel fire, simulating a vehicle blaze. Infrared cameras tracked temperature. Water mist systems activated within 8 seconds. The fire was suppressed in 40 seconds. Bulkhead doors sealed the section. Ventilation reversed, pulling smoke away from escape routes. The system performed exactly as designed. They ran the test 12 times with different fire scenarios. It passed every time. The tunnel opened in 2042. The first convoy of vehicles, escorted by safety crews and robotic monitors, crossed the Arctic underwater in 9 hours. Average speed, 45 kilometers per hour. Total cost, $25 billion. Cost per kilometer, $62 million. Cheaper than any bridge or tunnel of comparable length ever built. And it will last 100 years. This tunnel is not just a transportation link, it is proof of concept. Proof that humans can build permanent infrastructure in environments that were considered impossible a generation ago. Proof that advanced robotics and AI do not just make construction faster, they make construction possible in places where human workers cannot survive. This tunnel used self-healing materials that repair their own damage. It used autonomous fleets that worked for years without human presence. It used predictive AI that solved a structural crisis faster than human engineers could diagnose it. The techniques developed here are not staying in the Arctic. They are spreading. Underwater tunnels in seismically active zones are now using floating designs and smart joints. Offshore wind farms are using the same autonomous underwater robots for cable installation. Deep-sea mining operations are borrowing the same sensor networks and predictive maintenance systems. The Arctic Tunnel was a megaproject, but its real legacy is the technology it proved worked. And this is just the beginning. If we can build a tunnel beneath moving ice in the Arctic Ocean, what else becomes possible? Tunnels beneath unstable seabeds. Tunnels through mountains previously considered too risky. Infrastructure in deserts, jungles, and oceans where humans cannot easily work. The constraint is no longer the environment. The constraint is imagination and funding. So here is my question for you. If engineers can build this tunnel in the Arctic, what impossible megaproject should they tackle next? A tunnel through the Earth's mantle? A floating city in the open ocean? A railway to the moon? Drop your ideas in the comments. The future is not waiting. It is being built right now, in places you cannot see, by machines you have never heard of. And the next impossible project might be the one you suggest. Until then, remember, the impossible is just the future we haven't built yet. This is Future Factories, and we will see you in the future.